Hi everybody. In this video we're going to keep going with chapter 1 and we're going to look at section 1.2, sampling from a population. So let's jump right in. So I'll let you read the learning goals. Again, there are videos for these learning goals in your ebook if you need extra practice. So we're going to start here and we're going to define population and sample. So a population is all individuals or objects of research interest, and data are collected from a sample, which is a subset of the population. The relationship between a sample and its parent population is one of the most important ideas in all of statistics. So we are going to talk about samples and populations every day for the rest of this class. You absolutely have to understand this concept. So the idea here is that researchers want to learn about populations, but data ordinarily cannot be collected directly from a population because populations are too big or not well defined, and so samples are taken. And that's the idea. So your data comes from a sample usually. Data can come from a population, it just doesn't happen as often. And yeah, populations cannot be studied directly because they're usually too large or not well defined. One population could be all American adults, but this is too large to study directly, right? You can't get data just for any old study by getting data from 200 million people, right? Even the government only does a census every 10 years because it costs so much to do and it takes so long to do. So if you want to learn about all American adults, you're not able to obtain data directly from everyone. Another population could be LCCC students or all LCCC students. But this is not well defined. It's still a large population, but it's also not well defined. Should we count part-time students? What about full-time students who are temporarily taking a semester off? What happens is that if you're trying to learn about all LCCC students, trying to just identify the population, like who is in the population and who isn't, could be too difficult, right? So what ends up happening is that we usually don't even worry about getting data from populations, and we just use samples. And in most circumstances, we can only work with a sample from what might be a very large population. Samples are usually much smaller than the population. So that's also important to remember. Samples are small, populations are usually big. Samples can be studied directly using measurements, questionnaires, or other types of data collection. So data collection does apply to populations, but populations are usually just too big or too hard to get to. All right, example 1, restroom hand washing. To estimate what % of people in the US wash their hands after using a public restroom, researchers pretended to comb their hair or put on makeup while observing 6,336 men and women in public restrooms throughout the US. They found that 85% of the people who were observed washed their hands after using the bathroom. So what is the sample, and what is a reasonable population to which we might generalize? So this is a very common question early in chapter 1 like this. So what is the sample? Well, if you're not sure how to do this, before we look at the answers, just go back and look at this picture, right? The sample is a smaller piece of a large population, right? So let's look at that again. So the sample is a smaller group. So the 6,336 men and women in the public restrooms, that is our smaller group. So that's our sample. It's where the data comes from directly, those people who were observed. And what is a reasonable population to which we might generalize? So, as you're going to see, there's no simple answer to this. Now, the researchers want to estimate what % of people in the US wash their hands. So you might say the population is everyone in the US. But maybe you want to clarify that. we could reasonably generalize the results to everyone in the US who uses public restrooms. Maybe there are people who don't use public restrooms, and maybe their hand washing habits are different. But some of you might say, well, couldn't the population be something else? Sure. There's many, many answers. It could be everyone in the US. That wouldn't be my first choice. My first choice would be the one that I put up there. But other people could argue that maybe this does apply to everyone, even though people that don't use public restrooms were not able to be part of the sample. What about all people in the US who use public restrooms in the cities in which the study was conducted? Right? So there were 6,336 people who were observed in public restrooms, but that wasn't randomly spread out throughout the United States. It turns out this study was done in a few clustered areas. Grand Central Station, a Major League Baseball park, things like that. So maybe you're not comfortable generalizing to people in Kansas if nobody from Kansas was part of the study. This is another perfectly acceptable population. Or what about everyone in the US in a public restroom with someone else present? What if people act differently when somebody else is in the bathroom with them? So what I want you to take away from this is that sometimes there's no single right answer for a population, but there could be several reasonable ones. So in our class, you are not responsible for coming up with reasonable populations, okay? It's just too hard of an exercise to do because there are many, many correct answers. However, given the choice of two different things, one is a sample, one is a population, you need to be able to identify which one of the two is a sample and which one of the two is a population. But you're not going to have to come up with populations on your own. Let's keep moving. So the sample size, we attach the letter N. So notice that this is boldface, right? Boldface italics. So this is a vocabulary term. You have to know this. For the rest of the course, if you see the word sample size or you see the letter N, it automatically means the number of people or objects who were sampled. So in the example we just saw, N was 6,336 because that's how many people there were in the sample. Some of you might be thinking, this seems like a small sample compared to the size of the population, but it's actually considered to be quite large. And we're going to talk about that much later in the class, what constitutes a large sample. All right, let's keep rolling. Next up, statistical inference. So statistical inference is the process of using data from a sample to learn something about a population. Statistical inference is what we're going to do starting in Chapter 3 and for the whole rest of the course. So the first two chapters are mostly dealing with samples. After that, we start talking about populations. Much, much more than we have been or will early on. So look at the idea here. We want to learn about everyone in the United States washing hands, let's say. We collect data from the sample, right? And so in the example we just saw, 85% of the people in the sample wash their hands. But we want to be able to go backwards and learn about the population. So if we know 85% of the people in a sample wash their hands, what does it tell us about the population? So the information that a sample gives us about a population is statistical inference. Populations don't tell us anything about samples, but samples can tell us about populations. Yeah, in later chapters, we're going to learn precisely how much information a sample can give us about a population. The sample in example 1 would tell us that somewhere between 84% and 86% of the general population wash their hands after using a public restroom. So that sample gives us some information. How much information? It turns out is this, and that's what we're going to focus on starting in Chapter 3 and after. And that's called statistical inference. The sample tells us about the population. But how do we know that the sample can be used to learn about the population? How do we know we're allowed to use a particular sample? So there's something called sampling bias. That occurs when the method of selecting a sample causes the sample to differ from the population in some relevant way. Any conclusion drawn from a sample requires the sample is free from bias. If sampling bias exists, then we cannot trust generalizations from the sample to the population. So let's talk about the hand washing example again and see how this is relevant. If we want to learn about all US adults, restroom habits, and not everybody in the US was able to be part of the sample, then the results would be biased in some way. Maybe people in Ohio or Kansas have different hand washing habits than people in New York or Georgia. And so that would be sampling bias. And it turns out sampling bias happens all the time, and it's very difficult to get rid of. So one thing we can do to reduce sampling bias is take a simple random sample. And when we choose a simple random sample of n units, right, n is our sample size, each unit of the population has an equal chance of being selected. So a simple random sample is called a representative sample because it resembles the population only in smaller numbers. So in other words, it captures all of the characteristics of the population. Or we think it does. It's more likely to. A representative sample is more likely to be free from sampling bias than other types of samples. So it turns out there's lots and lots of types of samples. We're really just going to look at, is it a random sample or not? Right? That's really all we're concerned with in this class. Some of you might go on and take other stats classes later, might learn about other kinds of sampling. For now, that's the main one that we're going to look at. So how do we get a random sample, especially this simple random sample, where every unit of the population has an equal chance of being selected? If you're trying to learn about people's hand washing habits in bathrooms, a simple random sample would be impossible. Right? There's no way to observe everyone in a public restroom all the time, right? But other kinds of experiments or studies, we can get simple random samples, and that's what we're going to look at next. So how can we select a simple random sample of n equals 5 students in a class? So let's say there's 20 students in your class, right? Let's say we want to select 5 of them. And then I'm going to show you guys how to do that. And then we're going to talk about part B. What are some practical reasons why it would be difficult to select a simple random sample of 5 students from the entire LCCC student population? So let's say I need to select 5 of you guys in your class. So I could take volunteers, but that's not random. I could pick everybody's who, I could go alphabetically and pick the first 5 people alphabetically by last name. Not random. I could go by student number. Not random. There's only a few ways to get random samples. So the best way to do it is put everybody's name in a hat, or use another form of random selection, like assigning everyone in the class a number, then using a random number generator. So it turns out you have a random number generator, your calculator. That's what we're going to look at here in a second. So drawing names from a hat is perfectly random, right? Or it's random enough, right, that everybody has an equal chance of being selected. That's the idea. So why can't we use this method to select 5 students at random from the entire LCCC student body? Well, it's all of the things we talked about already, how the entire LCCC student population is very large, it's not really well defined, and it's too big, definitely too big to put everyone's name in a hat. In order to use a random number generator, we would need to have access to the entire list of students at LCCC, and we don't have access to that. So if you wanted to do some kind of survey or study of LCCC students, you would not be able to take a simple random sample. It just would be too hard. That doesn't mean that the study would be bad. It just means there might be some sampling bias, that's all. right? And the thing at the bottom, the bullet at the bottom is what we talked about earlier, right? Moving on. So now I'm going to show you how to use the random number generator on your graphing calculator to select a simple random sample of size n equals 5 from a list of 20 students in a class. So let's say there are 20 students in your class, and most classes are around 20 students. So here's how we're going to do it. Right. Oh, I messed up. Hold on. There we go. All right, so here's my trusty graphing calculator app. I gotta get back to it here. There we go. Okay. And so this is what we're gonna do. So hopefully you have your calculator handy or you have your phone app handy. And I'm gonna show you how to do this. So turn your calculator on, click the math button, and then notice it gives you some options. We're going to go over to probability, PRB. So just hit the arrow over until you get to PRB. And then we're going to go to option 5, rand int. So just go down to number 5. Okay, and then we're going to press enter down here at the bottom. Then type the smallest number in your list, the largest number in your list, and press enter. So if we're trying to select 5 students from a list of 20, then the smallest number that can be selected is 1, comma, 20, comma, 5, end parentheses, and then press enter. And so if I assigned everybody in your class a different number, this would give me a random selection of 5 students. And all of you are trying this at home. And if you haven't tried it yet, just pause the video here and get caught up to this point, and you'll see that you have different numbers on your calculator. So everybody could select a different simple random sample. And we're going to talk about random sampling a lot in this class, and I want you to think about this method. So the way that big, high-level professional studies are done, they usually don't carry a calculator around, but they might generate a list of numbers ahead of time and keep them sealed up. And then if they need numbers to randomly select something, they just open the sealed notebook or whatever and just read off a few random numbers. So this is the way to do it. It's really other than putting names in a hat, this is really the only way to get a random sample. All right, so let's go back. All right, so now we're going to move on and talk more about bias. So we talked about sampling bias, but it turns out that there are more general kinds of bias. We're not going to identify by name all the different kinds of bias other than sampling bias. But the word bias just means that the data were collected in such a way that it doesn't reflect the population accurately. That's all. It's not quite the same thing as what bias means in everyday life, right? Like a psychological bias or a cognitive bias. It's similar, but it's not quite the same thing. So the bullets at the bottom tell us 2 other kinds of bias. Bias can occur when people we have selected to be in our sample choose not to participate. So this happens a lot in surveys. You might want to get information from somebody and they might refuse to participate. Well, that's going to bias the results because that person is representative of the population in some way and their data is not counted. And bias may also be introduced if people do not answer truthfully. So that has to do with surveys again, right? Just lying in general or intentionally putting false information down. If the sample data cannot be trusted, neither can generalizations from the sample to the population. So we're going to look at example 3. Are the results biased or not? Indicate whether we should trust the results of the study. Is the method of data collection biased? If it is, explain why. ask a random sample of people in a given school district. Excellent teachers are essential to the well-being of children in this community, and teachers truly deserve a salary raise this year. Do you agree? So we would collect data from this and use the results to estimate the proportion of all people in the school district who support giving teachers a raise. So what do you think? So if you're not sure what's going on, pause the video and think about, do you think that this is a valid way to get data from a sample? And if it's not a valid way, what is exactly wrong with it? So I'm going to give you the basic answer on the next slide, but I want you to think of why, specifically why, the answer is what it is. So for sure, we should not trust the results of this study. The method of data collection is biased by the wording of the question. So it's what's called misleading wording, but I want you to think about exactly what is misleading about it and exactly what's wrong with it. Many people would answer differently than if the question had a neutral wording or listed all of the options available. Right? So the way the question is phrased, it doesn't appear as if there's any choices. So good survey questions will list choices, or the wording should be neutral. The wording should not introduce ideas that were not already in the subject, so the person being interviewed. You shouldn't put ideas into somebody's head and then get information from them, because the information will be biased. So think about specifically what is wrong with this. You're going to see this problem again. Let's do another one. Here is a professor survey. So in a sample survey of 305 professors at the University of Nebraska, very large college, 94% of them describe themselves as above average teachers. All right, so let's answer these questions. What is the sample and what is the population? Let's just start there and do this one. So remember, the sample has to be a smaller group than the population. Well, the sample is whatever we get the information from directly. Here we're getting the information directly from these 305 professors. So the sample is the 305 professors. That means the population has to be some larger version of that sample. So it has to be all the professors either at that college, or all the professors in the United States, or all the professors in the world. But we should probably restrict it to just professors at the University of Nebraska, because you don't want your results to be biased. Right? People in Nebraska, professors in Nebraska might act different than professors in Ohio. Based on the information provided, can we conclude that the study suffers from sampling bias? So if you're not sure, pause the video, think about it. I'm going to drink a little bit of tea. So there is no sampling bias, or if there is, we can't tell. Remember, sampling bias is when the sample fails to reflect the population. But if these are, in fact, randomly selected professors, then they will represent all the professors at the college. So we have no evidence of sampling bias. That doesn't mean it's not there. We just can't conclude that it is there based on what we're told. We're just not given enough information. Part C. Is 94% a good estimate for the percentage of above average teachers at the University of Nebraska? So the answer to that part C is clearly no. And on the next slide, we'll see why. So part C here is a very special sort of bias, where it's self-reporting bias or self-describing bias, where it's a psychological phenomenon that most people think they're better than average at most things, right? So a majority of people think that they're above average drivers, which is clearly impossible. A majority of people think they're above average spellers or bowlers. You name it. If you pick something and ask somebody if they're any good at it, or ask them if they're above average, more than 50% will say they're above average. It turns out that in this particular survey, it was 94% of these teachers thought they were above average, which is clearly impossible. So definitely biased. Not sampling bias, just a special kind of self-reporting bias that doesn't have a special name for us. All right, last example, finding bias in data. During World War II, the U.S. military collected data on bullet holes found in B-24 bombers that returned from flight missions. The data showed that most bullet holes were found in the wings and tail of the aircraft. Therefore, the military reasoned that more armor should be added to these regions as they are more likely to be shot. Abraham Wald, a famous statistician of the era, argued against this reasoning. In fact, he argued that based on these data, more armor should be added to the center of the plane, not the wings and tail. So what was Wald's argument? So what was his reasoning? So again, this is another one I want you guys to think about. I'm not going to tell you the answer to this one. You will see this problem again as well. And just try it. Just come up with things he might be telling the generals and stuff, because they're ready to reinforce these aircraft. And he's telling them, don't do it. You got to reinforce it in other places, not the places that are being shot. What kind of reasoning is that? And that's what we call finding bias in data. So the data are the bombers that came back with bullet holes in them. And Abraham Wald was able to see that this is biased data. Right? So think about what's the sample, think about what's the population, and then think about, does the sample represent the population? Okay, so that's it for section 1.2. Here's some stuff that these are just concepts that you're going to see over and over and over again. And of course, if you need extra practice, here's the list of topics. I do want to point out something, that this problem number 63 in the book is a homework problem, and it gives students a lot of trouble. So this is one you're going to want to look at all these, but this one you definitely want to take a look at. Just because it's kind of a goofy problem, but the answer's in the book, so you might as well look it up. All right, well, that's it for this lesson. So I'll see you guys next video, and until then, study hard, and bye-bye now.